Alright guys, welcome back to the mock examination for the Cambridge International ASNA level examinations 9701. This is paper 4.2. So we're going to have a quick go through over this paper. And yeah, we're going to try and solve it. So yeah, let's begin. So we're going to start off with question 1a. So it says define a transition element. So this one, we're going to be very straightforward, nothing too difficult. We're going to say that it is an element that forms one or more stable ions when that has incomplete 3D, this is important, 3D orbitals. So as long as you write that, it's a one-mark question, you don't have to worry too much, but these are the two things you need to mention. The one or more stable ions and has incomplete 3D orbitals. Define the term degenerate. So for this one, we're going to be going very simple. It is that all the orbitals are at the same energy. So as long as you've got that written down, then you've got one mark, easy peasy. So now for the electronic configuration of, remember, this is copper 2 ions, so you're gonna lose 2 electrons from that. So keeping that in mind, let's move forward. It's gonna be 1s2, 2s2, 2p6, after 2p6 is always 3s2, and then 3p6, and finally it's gonna be 3d9. Alright, very simple, nothing too complicated. So the aqueous solutions to the two copper 2 complex is shown below. So first of all, if you got anhydrated copper ammonia, so this will be a nice, beautiful royal blue. And obviously for copper chloride, you're going to go with a nice, bright, you don't have to write bright, but just write yellow. One of the more important questions for the A-level examination, explain why aqueous complex ions of transition elements are usually colored. So this happens because let me just get all that correct, there we go. The d orbitals are all in different, all have different energies. So when the electrons become excited, when light falls upon them, they absorb different wavelengths, and as a result, different colors are seen. Different colors are seen. Alright, so your 3 marks are for writing that they have d orbitals have the different energy. The electrons become excited is another one of your marking points, and you have to mention that not only do you have to mention that they absorb different wavelengths of light, but you also have to mention that because of that, different colors are observed. So the next question is, when an excess of ammonia is added to a solution of copper chloride, when it's formed, state the type of reaction, complete the equation for this reaction, state symbols are not required. So you can write a bunch of different things. You could say this is a displacement reaction, a ligand exchange. I'm just going to go with a nice substitution reaction. So over here, we know that you're going to add ammonia. So this will be NH3. Well, actually, first you're going to have to add another thing over here somewhere, but ammonia over here. Is that to solution of copper, added to a solution of copper chloride? So we need to figure out where the water comes from, right? So for that, we're going to add over here. We aren't going to balance it yet. We're going to wait and finish the reaction and then see what we have left over. So you've obviously displaced the chloride, right? So at the bottom end of this, you're going to have 4 chloride ions. That's pretty self-explanatory. And let's take a look at what we've got over here. So it says 2H2O. So this should be very simple. Just put 2 over here. And they say you've got 4. So you've displaced 4 chloride ions. Ammonium. So the ammonium ions are going to replace all that chloride. So you're going to put a nice clean 4 over here. And you're good to go. All right. The copper, anhydrous copper ammonium shows 3D stereoisomerism. Complete the 3-dimensional diagrams in figure 1.1 to show the 2 different stereoisomers. So this is going to be interesting. Remember that stereoisomers are basically, they're non-mirrored, so it doesn't matter how you're going to show it. So the way you're going to do this is, you can do this in any order. I'm going to do it this way. I'm going to do a bit like this to show. Remember, there's 4 ammoniums that you need to show. So there's 1 ammonium here, 1 ammonium there. You're going to draw like this. You can color that in. If you color it in, it's sort of easier to decipher for them. And NH3 over here, and then NH3 over here. And we still got 2 more water H2O bonds, so I'm going to do another one over here. And this will be very simple, H2O. And this one will also be like this. This is the one that's behind, and that will be H2O. So now for the stereoisomer one, you're going to have to create it in such a way that it's not a mirrored, that you can't really reflect onto it, right? So, same shebang over here. This one's going to be in the back. This will be NH3. This will be NH3. And then sort of color that in. And if you color that in, and then you put, so this is the difference over here. The H2 is going to go over here. Sorry, this will be OH2, my bad. OH2, because it's bound to the oxygen over there. So this will be NH3. Again, same deal over here. This will again be H2O. And remember, the O is sort of the one that's bonded over here. So then that for the final NH3. So we're going to have to take a look at, we're going to have to explain, deduce which stereoisomer in D2 is polar, and we have to explain deduce which isomer in D2 is polar, and we'll have to mention which one, and we'll have to explain why. Right, oh my god, I forgot to mention, so obviously when you have the same type of functional group on the same side of the bond, so we're going to label this as our cis isomer, and this one is on the opposite side, so this will be our trans isomer. So again, because the dipoles don't cancel on a trans isomer as they do on a, since the bonds don't cancel on a cis isomer as they do on a trans isomer, our polar isomer is going to be the cis isomer. And we're going to mention that the dipoles don't cancel. The cis isomer as the dipoles. Oh, sorry, so that's going to be over there. Cis isomer. The dipoles don't cancel. Oh, very simple. The dianion P can act as a tridentate ligand. Suggest how P can form 3 dative covalent bonds. All right. So let's take a look at what we've got over here. So this oxygen has 1 negative charge. This oxygen has another negative charge. And so we've got 1 nitrogen. So if we take a look at the bonds that are formed over here, let's not take a look at that. So we've got the 2 oxygen and the 2 nitrogens. So the 2 oxygens and the nitrogen can all donate 3 lone pairs of electrons to a metal ion. There we go. 2 moles of dianion P react with 1 mole of aqueous cobalt ions to form 1 mole of complex ion Q. So since we know that, it can form 3 dative covalent bonds, and cobalt over here has 6 molecules of that, so we're going to have to take a look at how many different 2 moles react with 1 mole of aqueous. So nothing too complicated about this. You've got 2:1 ratio, so this will be cobalt, and then you give your bracket, so 1 mole of cobalt, and then, so let me use a different third bracket just so you guys will understand. So cobalt, bracket C4H5NO4. Again, this is nothing too difficult. It's 1:2, so it'll be like that, and then overall charge will be minus to form 1 mole of complex ion Q. All right, very simple, nothing too difficult. And we're down to a definition. So, shows the values of the stability constants of some silver 1 complexes. Define the stability constant of a complex. So, very simple, we're just going to write it down. It is the equilibrium constant for the formation of a complex ion, in a solvent. Very simple, nothing too difficult, nothing too complicated. Use the information in table 1.1 to identify the most stable silver 1 complex. So, very simple, we're just looking for the largest value of the equilibrium of stability. So, if you take a look at that, obviously there's one that is a clear answer. You got 13, 7, and 18. So, this is obviously the largest. So, the most stable is going to be silver cyanide. C2 minus aqueous, and it has the largest constant, has the largest stability constant. There we go. It's a long question, but it's nothing too difficult or nothing that we can't figure out by ourselves, right? Sodium sulfite uses food preservative. A 3.75 gram sample of impure sodium sulfite is dissolved in distilled water and made up to 250 centimeter cubes in a volumetric flask. 10 cm³ of the solution requires 18.7 cm³ of acidified 0.015 mole per dm cube manganate ions to reach the endpoint. The equation for the reaction is shown. Calculate the percentage by mass of sodium sulfite in the sample. So it's a 3-mark mole question, so let's take a look at what we have to do. So it's a molar calculation, so let's first take a look at what we have. So we have the mass of impure sodium sulfite that is dissolved in distilled water and made up 250 cm³ in a volumetric flask. So what we first figure out is sort of the concentration of the moles of sulfite that we have in the distilled water. So nothing too difficult that we're going to have to figure out over here. But I think first of all what we're going to do is, since we have it, is figure out the moles of manganate. So this is going to be N is equal to volume into concentration. So our volume is 18.7, and because it's in cm³, it's going to be into 1,000. So you're going to multiply that with 0.015, and let me just input that into my calculator. So this is 0.015 into 18.7 divided by 1,000, and that gives me 2.805 into 10 to the power minus 805 into 10 to the power minus 4 moles. And if we take a look at the sort of molar, let's take a look at the molar ratio. So you need 2 moles of this to balance 5 moles of this. So the moles of sulfite that you have is going to be 2.805 into, first of all, you're going to multiply it into 5, because that's molar ratio, and then divide by 2. So this is the unitary method. So it basically goes, if 2 moles is equal to, if 2 moles is equal to 5, then 2.80, then 1 is equal to 5 by 2, and 2.805 times 10 to the power minus 4 is equal to 5 by 2 times that. So 2.805 into 5 into 10 to the power minus 4, and let me just put that into my calculator, and you should get 7.0125 into 10 to the power minus 4. Now remember, this was only in the 10 cm³ solution. So we're not done yet, because we need to figure it out in the sample. So the sample was 3.75 grams that we dissolved and made up to 250 cm³, right? So we have to first figure out how many is in the 250 cm³. So for that, that shouldn't be overly complicated. So we've got our value over here, right? We've got, so we know that 7.0125 moles of it was in 10 cm³. So in 250 cm³, it's going to have 7.0125 into 10 to the power minus 4 divided by 10 into 250. And that comes out to 0.0175 moles of sulfite. So we're not done yet. So this was the moles that reacted with the manganate over here, right? So now we need to figure out how many moles of this was in the solid. So we're going to need to figure out the sort of MR of sodium sulfite. So just give me 1 second while I get that ready. Right, so we're going to figure out the MR of Na2SO3. So that'll be 2 sodium. So sodium over here is 23. So that's 23 times 2 plus sulfur is 32.1 plus 32.1 plus, and oxygen is of course 16, 3. So that means that it totals to 126.1. So now let's find the mass of sodium sulfate that was actually in the sample. So 0.0175 times 126.1, and if you do that into 0.0175, we're going to get 2.206 grams. So because you got 2.220, well, it's actually going to be 2.207 if you round it out. But anyways, so remember that you first initially had 3.75 grams. So the percentage by mass is going to be 2.207 divided by your original amount, which is 3.75. So, and then you multiply that by 100. So 2.207 divided by 3.75 into 100 is going to give you 58.9%. You can write 59%. You're not going to be penalized for that. So we're going to put that over here. It's going to be 58.9%. And we're done with question 1. Hopefully it wasn't too complicated. Hopefully you guys were able to get it done. Let's move on to the next question. Solutions of group 2 hydrogen carbonates decompose on heating to give the corresponding metal carbonate, carbon dioxide, and water. So they've already told you what it forms. So now you just need to answer a very simple question. Write an equation for the decomposition of strontium hydrogen carbonate. So you're going to get the metal carbonate, you're going to get carbon dioxide, and you're going to get water. So first let's write this here, SrHCO3 and then 2. So you're going to get the metal carbonate. So you're going to get strontium CO3. You're going to get carbon dioxide. So you've already used up one of your CO3s. So you're going to get very simple, just one CO2. And very simple, you're going to get H2O. Nothing too difficult, nothing too complicated. So now they're asking, the thermal stability of group 2 carbonates increases down the group. Explain this trend. So as the radius of the charge density, when you're going down the group, the radius of the cation, or the radius of your group 2 metal increases, right? So because the radius is increasing, the charge density of the cation decreases. And because of that, it has a less polarizing effect, or it distorts the anion less. So you're just going to write that down. So you can either write, because as the radius of the cation decreases, the charge density of the increases, my bad. As the radius of the cation increases, the charge density decreases. And has a lower polarization on the anion. Polarization on the anion. There we go. The hydroxides and fluorides of group 2 elements show similar trends in solubility. Describe the trend in the solubility of the fluorides of calcium, strontium, and barium. Describe the trend of solubility of the fluorides of hydroxides and fluorides of group 2 elements show similar trends in solubility. So describe the trend in solubility of the fluorides of calcium, strontium, and barium. So because we know that in terms of hydroxides, your calcium hydroxide is the least soluble and barium is the most soluble, it's going to become the same over here because they say that they show similar trends. So your least soluble over here is going to be calcium fluoride over here, CaF2. Then it's going to be strontium, fluoride, and finally it's going to be barium fluoride. And now to explain why. So over here, you need to mention that both the lattice energy and the, well, actually one sec, let me think this through. All right, so got the periodic table over here. I was just taking a look, making sure that I didn't mess anything up. All right, so when we're talking about sort of solubility, there's two things we want to know. We want to know about the lattice energy, and we want, the lattice enthalpy, and we want to know about the hydration enthalpy. So as you're moving down the group, we've already explained this in the previous question, right? As the radius of the cation increases, charge density increases, and it has a lower polarization on the anion, right? So in the same way, as the size of your metal cation increases, your lattice enthalpy and the hydration enthalpy, they're both decreasing. So let's first mention that. As you go down the group, the lattice enthalpy and the hydration enthalpy. So remember, you can't say it becomes less, you have to say it becomes less exothermic. They're giving out less energy. Hydration enthalpy become less exothermic. So because they're becoming less exothermic, you also need to mention that the degree to which they're both changing. So as we're dealing with fluorides, it's relatively small and it's constant throughout all of these things, right? So as it's a small anion, your lattice enthalpy decreases faster than the hydration enthalpy. So you're going to have to mention that the lattice enthalpy becomes, now here's the thing, you have to say less exothermic more rapidly than the lattice enthalpy becomes less exothermic more rapidly than the hydration enthalpy. So we've got 2 points down, and our last point is going to be, as a result, the because of this, the enthalpy of solution becomes more exothermic. All right. Very simple, nothing too difficult. And we're down to define the enthalpy change of hydration. So this is very simple, a standard definition. The enthalpy change when 1 mole of gaseous ions, 1 mole of gaseous ions dissolve in water to form a solution. Dissolve in water to form a solution. Boom, very simple. State the main factors that affect the magnitude of the enthalpy change of hydration. Explain your answer. So there's two things that are going on over here, your ionic radius and the ionic charge. So as your ionic radius increases, there's less attraction between water molecules and gaseous ions. And as the ionic charge increases, your enthalpy, there's more attraction between the water molecules and gaseous ions. So you have to mention both of those. The main factors are, so we're going to write down ionic radius, ionic radius as the more it increases, the charge density decreases. The charge density decreases. And there's less attraction. Between water molecules and the gaseous ions. And then you're also going to mention ionic charge. Ionic charge, so this is sort of in the same vein. As the more it increases, so this will be the opposite. So as the more it increases, charge density increases with it. As the more it increases, the charge density increases, and there's more attraction. Between water molecules and gaseous ions. Very simple, nothing too complicated. Table 2.1 shows various energy changes. Use data from the table to calculate the enthalpy change of solution for magnesium fluoride. Oh, okay. So this is going to be an enthalpy, so let's figure it out. Lattice energy is minus 2957. The enthalpy change of hydration is minus 1926. And the enthalpy change of hydration of fluoride is minus 505. So it's good that we have all those figures together. So now let's put them together and try and get our answer. So for this, we're going to use Hess's law, obviously. We're going to use Hess's law. So that states that your del H solution is equal to the del H for lattice energy plus the summation of your del H of hydration. So your lattice energy over here is going to be minus 2957 plus, so we're going to take a look at what we've got over here. Well, no, since you're since over here, so your del H of energy, so this is going to be as it's dissolving in, so this is going to turn to positive. So this is going to 2957 plus, and if we sum up all the hydration, so it's minus 1926 plus, so this will be minus 505 times 2, and then if we do the math, so it's 2957 plus, so this will be minus 1926 minus 505 and 2 because there's obviously 2 fluorine ions over there, so this will be minus 2936 So if you do that, plus 2957, you're going to get a nice plus 21 kilojoules per mole. So this will be plus 21 kilojoule per mole. Nothing too complicated, nothing you have to worry about. The mercury 1 fluoride is sparingly soluble in water. The cation exists as a diatomic ion, mercury 2 plus with a covalent hydrogen mercury-mercury bond. Write the expression for the solubility product KSP of Hg2F2, include the units. So units obviously we know is going to be mole per dm cube, and this one over here, so we got 2, so because we got 2 plus over here, we're going to put Hg, we're going to put Hg2 2 plus, and we're going to have fluorine with its negative charge over here, and remember you've got 2 ions of that, so there you go. So it's over here, right? Hg2 2 plus, so you're going to need 2 moles of that, and when you do that, it comes out to that. So the solubility of mercury 1 fluoride is 9.2 into 10 to the power minus 3 at 298 Kelvin. So calculate the value KSP of mercury 1 fluoride at 298. So obviously we've got a 2 square over here, so because you got 2 moles of that, so it's going to be 2 squared times 9.2 into 10 to the power minus 3. And that'll give you a nice clean value of 3.11 into 10 to the power minus 6. So 2 squared because obviously you got 2 moles over there. So moving on to the next question. Solid manganese 4 oxide catalyzes decomposition of hydrogen peroxide. So state the decomposition of hydrogen, state the type of catalysis for this reaction. So this is, if you take a look, you got aqueous and then turns into liquid and gaseous, so obviously this is going to be heterogeneous. As the products are in a different phase to the reactants. Products are in a different phase to the reactants. So hydrogen peroxide reacts with iodide ions in acidic conditions as shown. The initial rate of this reaction is investigated with different concentrations of hydrogen peroxide, iodine ions, and hydrogen ions. Results obtained are shown in table 3.1. Use the information in table 3.1 to deduce the rate equation for this reaction. So we're going to have to figure out which one will be in first order, which one will be in 0 order, and so forth. So we're going to have to take a look at what happens at the rate whenever we add different concentrations of hydrogen peroxide, iodine, hydrogen ions. So let's take a look at what happens at the table. So we can see that for experiment 2 and for experiment 3, experiment 2, our hydrogen peroxide is the same. Our iodine is the only thing, our hydrogen is also the same. So let's use a different color. So let's say blue is for when it's same. So these are the same, and these are the same. So you'll notice that when the amount of iodine is doubled, so this is times 2, the rate also doubles, isn't it? So it's sort of an interesting observation, right? So iodine, in this case, because it's very linear, if it doubles, the rate of reaction doubles. So you can say that with respect to iodine ions, it is first order. So now let's take a look for hydrogen ions. So because we already know what happens with iodine, where the rate sort of doubles, right? So because we got hydrogen ions that are the same everywhere, let's take a look at sort of the first one, and let's take a look at the fourth one, because the hydrogen peroxide is the same amount. So these two are the same. Whereas this, let me just do that, 0.05 divided by 0.0125. So that's a times 4 increase. And I can already tell that this is a times 4 increase. So it's a different color because we're doing that. So those are the same. So let's use green. So this is a times 4 increase. And this is also a times 4 increase. So what happens for the rate? It goes from, so let me put that in, divided by 2.42. That is a times 4 increase. So that is very interesting. So you'll notice that even with the amount of hydrogen ions doubling by increasing by 4, the initial rate is still just times 4. So it's not increasing by any further than that. So because we know that the iodine already is a first order, because the amount of hydrogen ions isn't changing the rate of reaction any further, we can conclude that this is 0 order. And iodine, we're just going to write over here, first order over here. So wow. So that was a very interesting observation that we've got over there, right? So let's take a look at what happens. Now that we know that our hydrogen is a 0 order, so what about hydrogen peroxide? So what happens when we increase sort of, let's look for an experiment where we've got a change in hydrogen peroxide and we've got the same amount of iodine. So that's 3 and 4. So let's use pink for that. So this sort of doubles, times 2. This stays the same. And we know that hydrogen has no effect. So this then becomes times 2. So this is linear as well, so this will be first order. So the way we're going to write this down, very simple, is using references from experiment 1. Let's start with iodine. So using experiment 1 and 4, where H2O2 and, well, actually we were looking at 2 and 3, right? So how about we do that? So we're looking at experiment 2 and 3, where H2O2 and H plus are the same. When the concentration of iodine, I minus, doubles, the rate doubles. So iodine is first order. Then, looking at experiment 1 and 4, where H2O2 is doubled, is the same, but I minus and H plus is increased by factor 4. The rate only increases by a factor of 4 due to iodine. So H plus is 0 order. And then using from experiment 3 and 4, where I is constant when concentration of H2O2 is doubled, rate doubles, so it's first order. And then we're going to write the rate is going to be, let me just write it down over here. Rate equals K, and then you're going to put H2O2 and iodine. And there we go. Simple as. So now we have to figure out, using the rate equation from B and the data from experiment 1 to calculate the rate constant for this reaction, include the units of K. So we can use any one for this. So how about we stick with 2.42. Let's stick with experiment. Start with experiment 1. So 2.42 into 10 to the power minus 3 into 10 to the power minus 3 is equal to K times 0.045 times 0.03. And then if you do the math, so let's see, you should get to around 1.79. So this comes to around 2.42 into 10 to the power minus 3 divided by 0.045 into 0.03 is 1.35 into 10 to the power minus 3. And if you put that in, you get 1.79. And your unit, of course, is going to be dm cubed per mole per second, because they're all first order. Dm cubed mole. Fun question. All right, rate of thermal decomposition of azomethane is investigated. Figure 3.1 shows the results obtained. The reaction is first order with respect to azomethane. Use figure 3.1 to calculate 2 half-lives to show that the reaction is first order. All right, so let's take a look at this. So for this, we're going to take a look at where the concentration starts. It starts at 0.05. So let's first find out the first half. So that's going to be 0.025. So let's zoom in. So 0.0222. Oh, okay, that is too thick. Let me go a bit smaller. So this is 22. This is 24. So this is 0.025, which neatly comes to around 60 seconds. So now we're going to have to figure out what is 0.025 divided by 2. So if we do that, that comes to around 0.0125. So 0.0125. So 0.012, so 0.0125 is somewhere here. So just extrapolate that a bit, and it should be around here. And if you drag this down, would you look at that? So 100, so this is factor of 1, right? So this is 10, 20, 30, 40, 50. That's 60, 70, 80, 90, 100, 110. This is going to be 120 seconds. So would you look at that? The time is linear. So because we're noticing that the 2 half-lives constantly increase, as they're constantly increasing, as they're a constant amount, we can tell that these are first order. The 2 half-lives, let me go back to this. The 2 half-lives calculated for 0.025 and 0.0125 are the same time of 60 seconds, so it is constant and therefore first order. So use your answer to C1 to calculate the rate constant for the decomposition of azomethane. So it's going to be ln 2 divided by the half-life, which is 60. And if you do that, you're going to get 0.0116. 0.0116. 0.0116. Describe the effect of increasing temperature on the rate constant and the rate of reaction. So the rate of reaction is going to increase. So both will increase. So we're moving on to now writing down. Cobalt is a transition element which forms compounds containing cobalt plus and cobalt 3 plus ions. Cobalt sulfate dissolves in water to form a solution containing the cobalt hydroxide complex ion. Complete the electronic configurations of cobalt 2 plus ion and cobalt 3 plus ion. So this is interesting. I hope you guys remember that this is the trick for this question, where cobalt 2 plus is 3d7, but cobalt 3 plus is 3d6. So we've already answered this before, so I'm not going to do it again. But just to say it again, they have vacant d orbitals that are energetically accessible. Energetically accessible. Boom. An excess of concentrated hydrogen chloride is added to a solution containing cobalt. That describes the color change observed and state the cobalt containing product. The color changes from pink to blue because cobalt is least, and say the cobalt containing product is quiz. Write an equation for the reaction occurring in A3. So we're going to write down this over here. So it's going to be cobalt H2O 6 and has 2 plus, and it's reacting with 4 hydrogen chloride. So this is going to give us cobalt chloride 2 minus plus 6 H2O plus 6 free hydrogen ions. Alright, nothing too complicated. And this is very simple, a ligand exchange. Write an equation for the reaction that occurs when excess of sodium hydroxide is added. So this is going to be, we're just going to mention the ions that are happening, right? So this will be cobalt, cobalt H2O6 2 plus 2 hydroxide ions, which gives you cobalt chloride plus 6H2O oh, I'm so sorry, why did I write cobalt chloride? Sorry, my mind's still in the previous question. So this will be cobalt OH. So this will be cobalt OH6, OH2 plus 6H2O. So use the Nernst equation. Cobalt metal can be oxidized by acidified potassium manganate. The relevant half equations and their E values are shown. A cobalt electrode is constructed when cobalt is 0.02 mole per dm cube at 298 Kelvin. Use the Nernst equation to show that the E value for this cobalt electrode is minus 0.33. So we know that the Nernst equation is E is equal to E plus 0.059 by Z times log oxidized by reduced. So if you plug in your values over here, it's minus 0. So because you've already got the moles, which is over there, 0.02, so this will be minus 0.28 because we've already been told that 0.28 plus 0.059 divided by 2 into log 0.02, and that gets you minus 0.33 volts shown. Always fun to write shown over there. Calculate the value of the electronic cell. An electrochemical cell is constructed using the cobalt chloride electrode described in B1 and a Cr2O7 is used in which all conditions are standard. So calculate the value of the E cell. So this is fairly straightforward. You don't have to think too much about this. Your E cell is equal to E cathode minus E anode. So E cathode minus the electric potential at the anode. So it's going to be plus 1.33 minus 0.33 because we've already shown that, right? Show that the E value for the anode is minus 0.33. So even if you don't get this question, you can still answer. So it's 1.33 plus 0.33, which gives you 1.66 volts. Very simple. Nothing too difficult, nothing too complicated. Current is drawn from the electrochemical cell described in B2. Write an equation for the reaction taking place in the cell. All right, so this will be 3 cobalt plus Cr2O7 minus plus 14 hydrogen plus, which gives you 3 cobalt ions, 2 plus, 3 plus 2 chromium ions. So chromium is at a 3 plus, and of course water, 7H2O. Complete the sentences to identify the negative electrode and the direction of electron flow when a current is drawn from the cell described in B2. So this will be, ignore that, cobalt 2 plus, and cobalt is a negative electrode and it flows from the negative electrode to the Cr2O7, 7 minus, 2 minus, Cr3 plus electrode. A molten cobalt salt is electrolyzed using a current of 0.5 amperes. 0.547 grams of cobalt metal forms the cathode. Under the conditions used, no other reduction reaction occurs at the cathode. Calculate the time in minutes for which the current flows to produce this mass of cobalt. Interesting question. So first let's figure out the moles of cobalt that we have. So cobalt is 58.9. So 0.547 divided by 58.9. And if we put that in, 0.547 divided by 58.9, you're going to get 9.29 at 10 to the minus 3, so that's 0.00929. 0.00929. So we've got the moles of cobalt. So now we need to figure out the coulombs that we need for this. So remember that it's 2 plus, right? So it's going to be moles 0.00929 times 2 times the constant, which we know is 96,500. 96,500, because of course it's 2 plus. So this gives you a value of 1792. So now we need to figure out, is electrolyzed under a current of that? So time required is just going to be this divided by the current, which is 0.5, which basically doubles it, and so you get, remember, this is all in seconds, so 1792 divided by 0.5 gives you 3584 seconds, but the answer is in minutes. So divide this by 60, and you get 59.7 minutes. There we go. And we're almost done with this paper. It's a very long paper, isn't it? That's what A2 is all about. It's a grind. Table 5.1 shows the structures of sections of 3 polymers, X, Y, and Z. Each polymer is made from only one type of monomer. So we got polymer X. Okay. And we've got polymer Y, we've got polymer Z. So complete table 5.2 to state the type of polymerization and draw the structure of the monomer for each polymer X, Y, and Z. So let's take a look at what's going on. I'm noticing that because this carbon over here actually looks like this. So it's got 2 hydrogens over here. And then the carbon sort of over here also has, this nitrogen also has 1. So because you're sort of seeing 2 carbons over, hydrogens over here, this makes me want to guess that this is a condensation. Condensation, polymerization. And obviously the structure of the monomer is going to be, so if we go up over here, I'll just write down in structural form. This is going to be H2. This will be CH2, 5, and then COOH. So I've already given you sort of the monomer over here, right? So 1, 2, 3, 4, 5. Sorry, let's not count that. So it's over here. So 1, 2, 3, 4, 5. And then that's the COOH. So yeah, that's how that's going to be. Y. So it's all with carbons, right? So you can safely assume that sort of these had double bonds with each other. So this will be addition. And for the monomer, it's going to be CH2 double bond CHCOO, CH3, CH COO, CH3. So you can tell when it starts to sort of, over here, CH with that, CH2 is bonded with CH with that. And the last one, Z, taking a look at it, This also feels like a condensation. Condensation. And in similar vein, this will be CH3, CHOH, COOH. There we go. So moving down. Amino acids can act as monomers. State what is meant by the isoelectric point of an amino acid. Very simple. pH where? pH where it behaves as a Zwitter ion. Behaves as a Zwitter ion. Very simple. A mixture containing, let's take a look. Table electrophoresis can be used to separate and identify amino acids. Table 5.3 shows information about 3 amino acids, glycine, lysine, and glutamic acid. So glycine has an isoelectric point of 6, lysine has 9.7, and glutamic acid has 3.2. A mixture containing these 3 amino acids is analyzed in a buffer solution of pH 6. Draw and label 3 spots on figure 5.1 to indicate the predicted position of each of these amino acids, glycine, lysine, and glutamic acid, after electrophoresis. So glutamic acid has an isoelectric point that is less positive than all the other ones, right? So because glutamic acid has the closest, has the lowest one, and the highest one is lysine, obviously. So lysine is going to move farther down. It's going to go more towards the negative pole. And you can sort of, if you look at glycine, sort of right in the middle. So I feel like glycine will be just a bit, so let me use different colors for this. So let's use blue for lysine. Lysine will be all the way over here. We'll write that down. Lysine. We'll use green for glycine. Over here, this will be gly. And we'll use red, good old red for this. This will be close to, so the positive one. So this will be for glutamic acid. So again, the lower the isoelectric point is, lower, closer to positive pole. Electrophoresis is repeated using a buffer solution of pH 11. Predict how the position of glycine will change, if at all, after electrophoresis. Interesting. So let's put in a buffer solution of pH 11. So because it's dissociating more in a pH 11 glycine, because it has the carboxyl group, it's going to dissociate a bit more, and so it's going to move towards the positive terminal. So we're going to write down, it will move towards the positive terminal. Move towards the positive terminal. Nice. We're at question 6. Write an equation for the methylbenzene reacts readily with nitronium ions, are generated by the reaction between concentrated nitric acid and concentrated sulfuric acid. Write an equation for the formation of the nitronium ion. Alright, so let's go. So this will be HNO3 plus H2SO4. So that's going to give you NO2 plus that's the nitronium ions formed. You're going to get a HSO4 minus, and you're also going to get a molecule of water. Nice. Complete the mechanism in figure 6.1 for the nitration of methylbenzene to form 1-methyl-2-nitrobenzene. So the organic intermediate. So let's keep going. So this will be like this. We got it over there. Remember, it's going to be half over here. And you've sort of got a positive ion over here. So let's label our carbons. 1, 2, 3, 4, 5, 6. And don't forget to show the branching chains as well. So you've got a CH3 over here. And don't forget to label it CH3. This is your H, and this is your NO2 that's forming. And then your curly arrow. Curly arrow is very important. Make sure you don't forget that. And then that's it. And you're going to release one entry. Very simple. Phenol can be nitrated with dilute nitric acid. Explain why the nitration of phenol occurs under milder conditions than the nitration of benzene. So, because if we're taking a look at the nitration of phenol occurs under milder conditions than the nitration of benzene. So, in phenol, there is a lone pair from oxygen that is delocalized and it overlaps with the ring. So because that's happening in phenol, whereas if you compare it with sort of benzene, where the ring is sort of stuck over there, so because this is happening, the electron density of the ring is increased. And so it's able to polarize electrophiles better. So, wait, I'm not sure I did a good job at explaining that, so let me just go through that again. So the main thing you need to know for this is that the hydroxyl group that phenol has, it's a stronger activating group. And because it's a stronger activating group, it's able to increase the electron density of the benzene ring, and thus it makes it more reactive towards electrophiles. Because the oxygen atom of the hydroxyl group in the phenol, it has a lone pair of electrons that's donated into the pi system of the benzene ring. So because the oxygen atom in this phenol, so if I were to draw sort of the, so this is sort of the oxygen over here. Let's say this is O, and this is with hydrogen. So it's got over here. So it's got like a lone pair of electrons over here. So this lone pair of electrons is donated into the pi system of the benzene ring. So because it's donated into the pi system of the benzene ring, what this does is it increases the electron density. So this pair of electrons is donated to the pi system, and as a result it increases the electron density. And as the electron density is increased, once you can increase the electron density, you're making it more reactive towards electrophiles. So the way you're going to write this is the lone pair of electrons from oxygen is donated or let's say instead of donated, let's write is delocalized and overlaps with the pi ring. Sorry, pi system. Increasing electron density and thus allowing it to polarize electrophiles better. Electrophiles better. Complete the equation in figure 6.2 for the reaction of 2-nitrophenol with sodium. So obviously it's reacting with sodium. So again, don't forget the ring. The ring, NO2. This is very simple, just NO2. and this will be ONA plus half of H2. Suggest 2-nitrophenol can undergo different reactions as shown in figure 6.3. Suggest reagents and conditions for reaction 1. So when it's going from this over here, this is being having an amine group added to it. So when that happens, you're going to need hot tin and concentrated hydrochloric acid, concentrated HCl, and obviously that is a reduction reaction. Reaction 2 is carried out at room temperature. Draw the structure of the organic product formed from reaction 2 in figure 6.3. So this is very and draw the ring as usual, the NO2 that's over here, and this OH is replaced with, you're going to have the O, and you're going to give another over here, and this is going out of the box. Try and keep it within the box during your examination. There we go. Name the mechanism for reaction 2. So this is nucleophilic addition elimination. Nucleophilic addition elimination. The nitrite group in 2-nitrophenol is electron withdrawing. Suggest the relative acidities of ethanol, 2-nitrophenol, phenol, and water. So explain your answer. So we're going to have to go from most acidic to least acidic. All right, so you can already tell which one is going to be sort of the most acidic, right? So the most acidic is going to be, let me first write it down, 2-nitrophenol. After 2-nitrophenol, it's going to be phenol. And then surprisingly, water is more acidic than ethanol. So why is this the case? So what we have to know is that the 2-nitrophenol, it has an aromatic ring and the nitro group in it, so we've already discussed it in the previous question, is electron withdrawing. So because it's electron withdrawing, it's able to pull electron densities away from oxygen atoms and thus delocalize whatever negative charge it has and makes losing protons that much more favorable. So because it's electron withdrawing, it's able to make losing a proton much more favorable and thus makes it more acidic. Whereas if you look at phenol, it's still more acidic than water and ethanol because it has a phenoxide ion. And that stabilizes any negative charge that forms because it's able to delocalize. So because it's able to delocalize and and overlap with the pi system, as we mentioned before, it increases the electron density. And for ethanol, it's the least acidic because ethanol has a positive inductive effect because it has an electron donating alkyl group. So if we were to write all of this down, 1 second. So we start with 2-nitrophenol. 2-nitrophenol has trying to figure out how I'm going to write this. A 2-nitrophenol and phenol have a delocalized pair of electrons from oxygen that overlap with the benzene ring, with the pi system, which increases the electron density in the ring. Making it easier to lose a proton or H+. So we've already discussed that. And for ethanol is weaker than water. As the alkyl group is highly electron donating. All right, and there we go, that's done. Name and classify 3 other functional groups in salbutamol in table 6.1. So let's do hydroxyl. So hydroxyl will be primary. We've got alcohol. We've got another hydroxyl, but this one is secondary. And finally, we've got amine, which is all the way over there and is secondary. Salbutamol reacts with bromine to form an organic product X. Draw the structure of X. So bromine is just going to be, so the way you're going to do this is you're just going to give a small Br here. And yeah, that's it. Plus hydrogen, if you want, over here. So since we have to draw the entire structure, Br this will be NH like that. Bump over there, HOH, and this one will also be OH. Yeah. So now we have to draw the structure of Y. So this is a very big question. But thankfully we were able to solve it, and we're towards the end. Salbutamol reacts with excess of to form organic product Y. So we're going to have to remove 2 hydroxins from the structure and instead replace it with chlorine. That was 4. So let me do it again. That. So instead of this being a hydroxyl, this will be chlorine. This will still be NH, and it'll have so you can keep the OH here, not an issue, but over here, this will be connected to a chlorine. All right, and we're down to the last question. So if you made it this far, congratulations. We're almost done. This shouldn't take too long. Bromine reacts with methylbenzene in the dark in the presence of a suitable catalyst to form hydrogen bromide and compound L. L is one of 3 isomers that can form this reaction. The mechanism for this reaction involves methylbenzene reacting with the bromine ion. This ion is produced when bromine reacts with the catalyst. Complete the equation for the reaction of bromine with the catalyst. So this will be bromine, and the catalyst is, of course, aluminum bromide. And you're going to get bromine ion and aluminum bromide 4 minus. One of the isomers of L forms in much smaller amounts than the other 2 isomers. So this will be the one with a methyl group over here. CH3, and you're going to draw the bromine over here. And this is because the methyl group has an effect. Complete the mechanism in figure 7.1 for the reaction between methylbenzene and the bromine ion. So over here, we're going to show a curly arrow. So I'm doing that. And then again. Sorry, this is going to be incomplete, my bad. Plus. So a bromine here, hydrogen here, curly arrow here. Don't forget the CH3. And then together you get the benzene ring is closed again. CH3, Br plus H plus. Identify the chloro compound that reacts. So this will be chlorobutane plus white precipitate. And the equation for this sort of goes C4H9Cl plus H2O gives you C4H9OH plus H plus and your chlorine ion. And the mechanism 2, you're going to get chlorine ion plus silver ion, which gives you silver chloride, which is the white precipitate that you see there. Explain the difference in reactivity of chlorobutane and chlorobenzene. So because chlorine has a delocalized lone pair of electrons, it gives it a partial double bond. There's a lone pair of electrons that what do you call it? Delocalization in the pi system. It has a stronger charge density. And causes the CCl bond to have a partial double bond nature. Double bond nature. And we're done with the paper. So hopefully you guys were able to solve this. Hopefully it wasn't too complicated. And feel free to let us know if you have any questions. And yeah, best of luck for the exam, and see you around.